Okay, so we're in chapter 4, and this is Math 140, in case anybody wanted to know, and we're starting on problem number 41. Because I'm recording it, it'd be nice to know what it is.
That thing's not turned on.
But you're not there. All right, that's a good idea. Let's push this button and see if that does any good. There, is that better? All right, now, a little bit of luck. I remember what we're doing. A consultant firm submitted a bid for a large research project. The firms initially had a 50-50 chance of getting the project. However, the agency which the bid was submitted subsequently requested a different information and indicated that 75% success of bidding, 40% of unsuccessful bids. Past experience. How could you have 75% success and 40% unsuccess? Interesting. The agency requested additional information. Okay, 1. What is the prior probability of the bid being successful? That is, prior to the request for additional information. Okay. 0.5. 50-50. What is the conditional probability of a request for additional information given that the bid will ultimately be successful? What is the conditional probability of a request for additional information given that it will be ultimately successful? Past experience indicates 40% successful if they do that and 40% unsuccessful. Conditional probability. Yeah, I'm not sure what they're talking about. Compute the posterior possibility that the bid will be successful given a request. Okay, so conditional probability given that the bid will ultimately be successful. Okay, I think B is 75%. Is what I think they're talking about there. Compute the probability that the bid will be successful giving a request for
I'm still curious, if 75% is successful, how are they getting 40% unsuccessful? That just doesn't add up.
Yeah, I'm not so sure I like that answer either. All right, so we'll make a thing here. We're gonna have event A, B. All right, so the probability of the event, we'll call it A1, A2, is, so the probability is 50-50 when I submit my stuff. When I get extra information, the probability will be 75 of being rejected. That'd be not being rejected. The probability that I'm asked for more information, given that I'm asked, the probability of being accepted, 7.5. given that I'm not asked. The agency in which the bid was submitted subsequently requested additional information on the bid. Past experience indicates that for 75% of the successful bids, so that's 75% of my 50-50 chance is what they're talking about. Okay. So if we read the English, we'd know what it's talking about. So 0.75% of the successful bids are picked. 0.75 successful bids were asked for more information. We don't know what that number is yet. We haven't figured that out. And C, the bid will be successful given a request is at 40%. 40% of the unsuccessful bids were asked. 0.4% unsuccessful. All right. Draw a picture. Wrong picture. Okay, so here we go. 50-50. Either get it or I don't get it. When I ask for additional information, okay, so I've asked for additional information. 75% of those selected are on this side. Well, they all have to be in here, because if I'm not selected, okay, so in here, these are the guys that are asked inside that circle. And I have 75% of the total inside that circle that were asked. And over here, 40% were asked. Okay. So now we come back up to these two lines. What is the conditional probability of a request for additional information given that the bid will ultimately be successful? I know it's going to be successful
So if he's not 75,
I'm thinking it's 75%. It's going to be successful. The conditional probability of a request for additional information, given that the bid will ultimately be successful. I'm thinking that that's 75%. 0.75. Because I know I'm successful.
Now, the only thing I'm confused about is it's asking for not the percentage that's gonna be successful, but it's asking for the probability that they're gonna request any information.
No, that's not what it's asking for. What is the probability of a request for additional information given that the bid will ultimately be successful? So I know I'm going to be successful, and I know that 70% of the successful bids were requested at. No, I think I'd go with 75% there. Now this next guy, what is the probability that a bid will be successful given a request for additional information? Okay, so I don't know that it is going to be to begin with. So I have 0.5% chance of it being picked. %40 of the unsuccessful bids requested additional information. Okay, I'm looking on page 182. And I'll come down. And we're going to apply what's there. So we have events. And the first event, 1 and 2, and 0.5, 0.5. So I was accepted, I wasn't accepted. Probability of those events. Conditional probability. The probability that I was asked okay, now I don't know that I was asked, given that I was asked. Okay, so what we want is we want the probability of A union B divided by probability of being accepted. So Hmm. I think I'm back to the 75 for B. Past experience indicates that 75% of the successful bids were asked for additional information. What is the conditional probability of a request for additional information, given that the bid will ultimately be successful? So if 75% of them are, then 75%, 0.75 would be that ratio. And now we're down to C, compute the posterior probability that a bid will be successful given a request for additional information. And we'll come back down to our thing here. The probability of success, 50-50. The probability of being asked to success. The probability of asked to not being successful. So this is the probability of ask intersection being successful divided by the probability of being successful. Okay, asked being successful is 0.75. So this would be 0.75 divided by 0.5, and this would be 0.4 divided by 0.5. No. The intersection of being asked and being successful. So I get a number greater than 1, that's why I can't do that. So now I have to ask myself, why am I getting a number greater than 1? 0.4 divided by 0.5, 0.8. But why am I not getting intersection being asked, being successful? Intersection of being unsuccessful, being asked, 0.2. try to do it somehow differently. All right, so I start here, and I'm 50-50. Percentage A1, percentage A2. Once I get to that point, I would then ask myself, was I asked? So 0.5 times 0.75, 0.35. No, I don't see it. Anybody want to help me?
That kind of made sense if you multiply the 0.5 by the 0.75. You have a 30% chance.
Yeah.
Well, we have a 38%
0.5 times
chance.
0.75 is 0.03.
0.5
75
times
would be 0.04.
Yeah.
0.375.
0.0375.
Yep, I think the best thing to do is move to the next question. What's the next question?
0.05 times 0.75.
50% is 0.5 though.
Okay.
Yeah. What's the next one? After
Oh, it
41?
would be 47.
47? And I'll go back and I'll rethink 41. Oh, is there? Oh, is there a 47? Oh, yeah, there is. A financial manager makes two investments, one in oil and one in municipal bonds. After 1 year period, each of the investments will either be successful or unsuccessful. Consider the making of two investments as an experiment. How many sample points exist in the experiment? Okay, so I have oil and I have bonds. And the oil can go up or down, the bonds can go up or down. Looks like I have, how many sample points exist for the experiment? After a 1 year period, each investment will be classified as either successful or unsuccessful. Consider the making of two investments as an experiment. How many sample points exist? Okay, so it's two experiments, one for, so each of them have two sample points up and down. Show a tree diagram and list the sample points. All right, so here's oil, there's bonds, and after 1 year, they're either up or they're down. So B is over there. C. Let O equal the event that an oil industry investment is successful, and M the event that the municipal bond is successful. List the sample points for O and M. Okay, so there's going to be O and not O, M and not M. So the C meaning the what does it mean? Complement, right? So I got O and not O and C and M and not M. List the sample points of the union of the events. So O union M. If I could go and make a U right. That's better. So I don't see how this is any different than the one before that, except I have a solution set. I have brackets around it. List the sample points of the intersection of the events. There's no intersection of the events. There are two separate events that are on their own. All events are the events O and M mutually exclusive. Yes, because you can't have one without the other. They have nothing to do with each other. Okay, next problem.
So hold on, what's exactly you want us to write down for B?
Hmm?
I don't really get B.
B is this. It's a tree
I
diagram.
don't even know what that says.
Well, there's an O for oil and a B for bonds, and they go either up or down.
It's the,
Want me to draw it prettier?
Can you?
No, but I'll try. So I have oil, and I have bonds, and after 1 year, the oil can go up to O or down to complement of O. Bonds could go up to B, down to complement of B. And those would be my sample points.
just out of wondering, the complement of B.
Yeah.
What's that for again?
Not B.
Not B.
So if it were a digital class, then not 1 would be a 0.
Oh.
True, the complement of true would be false. The complement of O going up is O going down.
Thank you.
Okay? Next problem?
Hold on, I didn't get F either.
Oh, you didn't get F either? Yes. Oh, D. Is there an F?
Oh, you said D twice, that's why.
Oh, okay. That's why you didn't get an F, because I didn't put down an F. Okay. Next problem?
Sorry. 53.
5-3. Reference again the data for the MBA new matriculations from above in exercise 52. Given that a person applied to more than one school, what is the probability that the person is 24 to 26 years old? Okay, so I look up above. 24 applied for more than one school. Yes, no. 24 to 26, we have 299 of them. Now we have to know the total. So 299 plus the 379 divided by 678. 299 divided by 678. 0.44. And we might even call it 0.441. B. Given that a person is 36 years or over, what is the probability that the person will apply to more than one school? 51 divided by the total of that group, 169, plus 51, 220. We'll call it 20.23. What is the probability that a person 24 to 26 years old or applied to more than one school, that a person what is the probability that a person is that or applied to more than one school. Okay. Okay, so we need to find the probability that a person is 24 to 26. Alright, so that would be the 299 plus 379 2
If you're looking for
6, 7,
probability
8
under 24 to 26, wouldn't you
divided by
divide that by all
2018.
and add it up?
Yeah.
Okay.
And it tells me what that is. It tells me that I have 2018 students, so I don't have to add them up. But that's not what I'm looking for. So I'm looking for this number. I need this number because it's an interim number for what I need. Divided by 2018. 0.336, we'll call that. So the probability that he is in that age group, or that you applied to more than one school. So now we got to go the probability applied more than one school. So now I'm going to have to add up the 207 plus 299 plus 185 plus 66 plus 51 808 2018 0.4. All right, then I need to know the probability that we're both in the in that age group and we applied to more than one school.
This is all for C.
No, I haven't calculated anything. I need these just to find the problem. But we already did that, and that's 0.441, right? 0.441. All right, so now that I have everything I think I need, the probability of 24 to 26 union applied more than one school equals the probability of being 24 to 26 plus the probability of applying to more than one school minus the probability of the intersection of 24 to 26 applied for more than one school. Now I don't like that number because I calculated it wrong. Okay, I did an and here, I want an intersection. Okay, so I want the intersection of applied for one school and being that age group. Okay, so that would be 229 divided by 2018. 229 divided by 2018. Fat fingered that key. 0.11. 0.11. Okay, so the union of the probability of being that age group and applied for more than one school is going to be 0.336 plus 0.4 minus 0.11. .62 66. Okay, we could have done it one other way. We could have added up. We could have added up 207 plus 299 plus 185 plus 66 plus 51 plus 379 and divided that by 2018. And we should, yeah, now that I think about it. But that would be required. Now it's only easier if I get the same number. 207 plus 299 plus 185 plus 66 plus 51 plus 379 equals divided by 2018. Said, now assuming I didn't fat finger a key, I get a different answer. And I get a 588 answer. So now the issue is, did I do that right? I still get the 588. So what is the probability that a person is that old or applied to more than one school? All right, so I like this 0.588 answer better. And now we'd have to go back up here and see why what we did here that we didn't like.
Would you get to 229 from the probability 24 to 26 and intersections. How'd you get the 2.229 for the 0.11? 229 over 2, that number, yeah.
Okay, so we got the intersection of the age and they were accepted. They applied to more than one school. So that intersection is the 229 number. So 229 out of the total is that age group did apply to more than one school out of the total.
Don't you mean 299?
Yeah, I think.
Oh, it's 299.
Yeah.
Well, that is a horse of a different color. Thank you very much.
And your answer would be 0.1. Yeah,
0.148,
0.15.
and then come down here, 0.148.
.58.
.588, which is exactly what we got going the other way. So yes, I agree that it would have been simpler to just add them up and divide by 2018, and I would have got the same answer either way. Should have been 299, and I had a 299. Yeah. Now delta. Suppose a person is known to have applied to only one school. What is the probability that the person is 31 or more years old? All right, so we got the probability. We know that he applied to more than one school, and he's 31 or older. Is known to have applied to more than one school. Alright, he's 31 or older, so I gotta go 193 plus 169 divided by the number of the no's. $201 plus 379 plus 268 plus 193 plus 169. Looks like 0.299. Is the number of schools applied to independent of age? Okay, is it independent of age? So this is a subjective thing. So in the age group 23 and under, they're the same. In 24 to 26, no is bigger. In 27 to 30, no is bigger. In the rest of them, no is bigger. And then in the 30 to 35, no is bigger by a lot. And in the 36 and up, no is even bigger by more. So now the issue is independent of age. As age goes up, I end up applying to less schools. So I think the answer is yes, it is. No, it's not independent of age. I would say no. This is dependent on age. As age goes up, you apply to less schools. And that makes sense. As we get older, we know what we want. No? All right, whatever. Do I have another one?
59 is the last one.
5-9. Let's hope for the best. An oil company purchased an option on land in Alaska. Preliminary studies say high-grade oil, medium-grade oil, no oil. What is the probability of finding oil? Alright, so the probability of finding oil would be 0.5 plus 0.2, which would be 0.7. So the probability of the high-grade oil plus the probability of the low-grade oil. Or we could go 1 minus 0.3, which is the probability of no oil, giving us the 0.7. So we go either way. After 600 feet of drilling on the first well, a test sample is taken. The probability of finding oil is identified as that, 0.2, 0.8, 0.2. How should the firm interpret the oil test?
If there's a medium quality
Yeah. What are the revised probabilities that there is that, and what is the new probability of finding oil?
$80.
It's interesting. I go and I do my oil thing. Yeah, I would feel very much more comfortable if my probabilities added up to 1, right? And right now they add up to 1.2. The probability of soil. At 200 feet of drilling on the first well, a soil test is taken. The probability of finding the particular type of soil identified by the test is as follows. Okay, the probability of having that soil and finding high-grade oil, 0.2. The probability of having that soil and giving medium-grade oil, 0.8. The probability of having that soil and having no oil is 0.2. All right, what are the revised probabilities? Okay. I'll do a tree thing. So I start at some point.
If you subtract the sample from the quality of oil from the original one, you would get 0.3, 0.6, 0.1, which would be 1.0. So therefore, it would be 0.9%, maybe.
See, what they're not telling us is they're not telling us the problem. They're not telling us the probability of the soil sample being found. They're saying that given that the soil sample is the right type, I have some probability. Given that the soil sample is the right type, I've got medium oil. Given it's the right type, I have no oil. But we're not given the probability that the soil's the wrong type. And so that is what concerns me at this point, that I'm missing a number that I really would like to have. Okay, so the probability of soil and high-grade oil, given high-grade oil, equals the probability of soil intersection high-grade oil divided by the probability of high-grade oil. Probability of soil intersection high-grade oil. Okay, that's what we're gonna do. Okay, so we want to know the probability of soil intersection high-grade oil, the probability of soil intersection medium-grade oil, and the probability of soil intersection no oil. Those are the things we're going to calculate. Those would be our new probabilities. And so the probability of soil high-grade oil times the probability of high-grade oil, 0.2 times 0.5. The probability of medium-grade oil, 0.2 times 0.8. The probability of no oil, 0.3 times 0.2. And I think I turned those guys around. Okay, so 0.2, oh, lost my calculator. 0.2 times 0.5, 0.1. 0.2 times 0.8, 0.16. 0.2 times 0.06. What is the new probability of finding oil? Once I get the oil sample, I think I would go with those things. So the new probability of finding oil. The old probability of finding oil was 70%, right? What is the new probability? Because see, we could still have the wrong oil sample and still have oil. It used to be 0.7, right? So it used to be 0.7. We're going to subtract away these guys, the union of the soil and the other guy, 0.1, 0.16, 0.06. .38. Do I like that? Or would we say, would we go the other way? You know, I sort of like that. I think it's low. No, not necessarily. So I have a 70% of chance of finding oil until I get to 200 feet, then my probability goes down of finding it because I have a test sample that doesn't like me. I got a better answer. We'll do what we did last time. We'll go 1 minus the probability of I have the soil that I'm looking for, but I have no oil. If I could spell soil right. So that'd be 1 minus 0.2, which would be a 0.8. I think I like that better. I had a 70% probability of finding the oil before, and now that I get down 200 feet and I check my sample that I have, and with that sample I have a 0.8 possibility to continue. If I don't have the right sample, I'm not going to continue at all. So I think I like that answer better for my last answer on part delta Bravo. So that'd be my last Bravo answer.
So, where'd you get those numbers then? The 0.1 and 0.2.
On page where is it?
What are you at?
Page 182. It says the probability, or the conditional probability of the event is equal to the probability of the union of the two events divided by the probability of the event. Okay, I rewrote it to say the probability of having the sample and having the union of those two things is equal to the probability of the sample in the event times the probability of the event. So that's how I got those partial things.
Right.
So that's how I got the probability of the union of sample being right and having that, sample being right and having that.
Right, I see where you got the 0.1 now. Where did
Yeah.
you get the 0.2?
Where?
In that. Go down.
Okay, so what you want me to do is you want me to erase
No.
these numbers and put them in the right order,
It's not,
Which
it's
I-
not
which
at all what I,
which I didn't do last time.
not at all what I said.
Yeah, but I still didn't do that, so I'm going to put them in the right order this time. So what I want is the 0.2 times 0.5, which is the high-grade oil. And then I want 0.8 times the 0.2, which is the low-grade oil.
Are you asking where he subtracted 0.2 from 1?
Yes. Thank you.
He just took that from the no soil reading on the second set of numbers. So basically the 0.2 cancels out the other, cancels out this.
Okay, so down at the bottom right here, is that right there?
Yeah.
I've drilled a well down 200 feet. I've looked at the sample of the soil, and the sample of the soil says that my probability is
Oh, is that
0.2.
one? Is that 1.0?
That's
Yeah.
one.
Oh,
One being the total
Gotcha.
possibility minus the 0.2 of no oil.
Okay.
Yeah, okay. Are we good with that?
Yeah.
All right. Emily has her hand up, sort of like she has a question.
Why didn't the bottom set of numbers equal 1?
Because we don't have all the probabilities. So the stuff that's not one is the not oil stuff. So you could, everything would add up if you had, oh, yeah, the soil sample things, why I had a 0.2, a 0.8, 0.2,
Mhm.
because that's not taking into account that, yeah, I don't know. I'd like to explain that to you, but I have no idea.
That's why it doesn't make sense to me.
Yeah.
Yeah.
Because if I had, that's why I said I'm not comfortable with those numbers not adding up to 1.
Okay.
And I'm still not comfortable with those not adding up to 1.
Because I just don't understand how the probability is 80%.
Yeah.
If you're taking it away from
Yeah.
1, it says 1 equal 1.
That's right. So I have a sample of the soil. So if I have the probability of having the right soil, given that I have the right soil, I have those types of things, and I agree with your analysis that those should have added up to 1, and at that point we may have just said forget the problem, move on to something else now. Okay, I'm going to start chapter 5, unless I hear any objections. I don't know if objections is the right word. And I'm sort of hoping that it gets weirder in chapter 5. We're not weird enough yet, are we? Oh, good. Only 48 transparency. So I only have to do 15 an hour, 30 an hour. Yeah, something like that. Okay. What I think we'll do is we'll stop. Aren't going to look at it anyway, right? Oh, it does matter. Oh, yeah, that's much better. So discrete probability distributions. What does discrete mean? Not continuous. So your watch, the clock on the wall, is a continuous thing. It's going around, but if it were a digital thing giving us numbers saying 1, 2, 3, 4, that'd be discrete. You could make a case that clock is ticking every second, and it's also discrete. So the second hand should move more smoothly to be continuous, because I can't have a 0.1 second by that clock on the wall. So discrete means things that aren't continuous. I can have a 1, I can have a 2, but I can't have a 1.2. So I can have a penny, and I can have 50 cents, and I can have $1, but I can't have $1.37.5 because I don't have any half cents. Yeah. Random variables, discrete probability, we're going to expect some value, binomial probability distribution. Okay, so we'll stop for a moment. And so I got A plus B, and I raise it to the 0 power. What do I get? 1. I have A plus B, and I raise it to the 1 power. What do I get? A plus B. I have A plus B, and I raise it to the squared power, and I get A squared plus 2AB plus B squared. A plus B cubed. A cubed plus 3 A squared B plus 3AB squared plus B cubed. This is a binomial guy. I'm now doing a binomial expansion of it. You have probably seen Pascal's triangle that looks like this. Maybe you have, maybe you haven't. Maybe you did back in 3rd grade. What am I doing? Boring you to tears. Yeah, so what I'm doing is I'm adding 1 and 5 to give me 6. I'm adding 10 and 10 to give me 20. And I'm continuing on down. 1, 7, 21, 35, 35, 21, 7, 1. So this would be a plus b to the 7th power would be a to the 7th plus 7 a6b plus 21 a to the 5th b squared plus 35 a to the 4th b cubed plus 35 a cubed b to the 4th plus 21 a squared b to the 5th plus 7 a b to the 6th plus b to the 7th. And going across there, I have an exponent of 7. 6 and 1 is 7. 5 and 2 is 7. 4 and 3 is 7. 3 and 4 is 7. 2 and 5 is 7. 1 and 6 is 7. So my exponents stay the same, and I can come all the way down to everything. And we use it for a probability of is the next card off the deck going to be an ace? Yeah, so we can use it in our gambling theory, yeah, and we probably will. So that's the binomial probability. Poisson's probability distribution is another one, and hypergeometric probability distributions. Oh, I just love it. Isn't that great? Just totally wonderful. So that's what we're talking about. So I have some random variable. So I have some experiment, and it's going to come out some way. So my experiment is flipping a coin. It's a head or a tail. I'm rolling a 6-sided die. I get a number 1 through 6. Some experiment. Discrete. We have a finite number of values and a finite sequence of those values. So when I roll a 6-sided die, am I going to get a 7? Ooh, I better not. Right? I have a discrete number. Continuous random variable, any number at all along the interval, an infinite number. Not good for us. Discrete random variables with a finite number of outcomes. So X is the number of televisions sold at a store, and it can be take on values 0, 1, 2, 3, and 4, because after I sell 4 televisions for the day, I go home because I made enough money. I'm not going to sell any more. We can count the TVs sold. They're finite. They have an upper limit. There's only 4 in the store, so that's all I can sell. The number that I have in stock. Discrete random variable. X is the number of customers in one day. 0, 1, 2. It might keep going. We can count the customers arriving, but there is no upper limit to the number of customers that might get there. Well, there has to be some upper limit. There's only 50,000 people in Council Bluffs, right? So, but it might go high. Random variable. So, family size. X depends on the tax return discrete. Distance from your house to a store. X is in miles. It's continuous. I could have 12.7 miles to the store. Do you own a cat or a dog? It's a discrete type of random variable. I have no dogs. I have a dog. I have a cat. I have both a dog and a cat. Those are my only possibilities to the question. You could say, well, gee, I have 5 dogs, right, and 3 cats, and well, you could make it more difficult. Discrete probability distribution. The probability distribution for a random variable describes how the probability are distributed over that variable. We can do it with a graph, we can do it with a graph function, we can do it with a table, we can do it with a function f of x. Oh, that'd be much more fun. The required conditions. Well, the function has to be greater than 0 at all of its points, and if I sum them all together, the probabilities, I have to have a 1. Okay, so can the probability, I'm flipping a coin, can I have a probability of minus something of my probability? No, I can't. So each of the outcomes have to be a value greater than 0. When I sum all the outputs, I better have a 1. So past data for TV sales. So units sold, number of days sold. I put it in a tabular fashion, and I have some function f of x. I took 80 and divided it by 250, divided by 210, and divided by 200. And then I probably put it in a graph, and you couldn't see the graph because the graph was colors on the graph are not good. Oh, that's better. Now I see the colors on the graph. Can you see the colors on the graph?
Yeah.
Wow. There, now you can see the colors on the graph. So now, but on discrete, I didn't sell 1.5 TVs. I didn't sell 2.5 TVs. I sold 1s and 2s and 3s. I think we should turn off half of these lights. If I brought in a step ladder, we could pick out some more of these light bulbs. Now I can understand why you sat there for 10 minutes without seeing anything, because you can't see it anyway. And here, when I sit up like this, I can see it very clearly, but when I was down the other way. Anyway, so I can make a graph. Discrete uniform probability. The simplest example of discrete probability is given by a formula. Okay. So the value of the random is more likely. The value is equal. Okay, so if I have n events, they're equally likely, then my function looks like 1 over n. Okay. The expected value, mean value, of a random variable is a measure of its central location. So I'm going to go in and figure out what the mean value is by taking the summation of the values that I've got times the probability of getting the value. The expected value is a weighted average of the random variable, and the weights are probability. The expected value does not have to be a value that is a random value. Well, if I take a weighted mean of something and I have 1, 2s, and 3s, I could get a 2.1, or I could get a 1.7. That's what they're talking about. Doesn't have to be one of those. Variance and standard deviation. Okay, so that's how I'm going to get my variance. I'm going to go and take the variable itself minus its mean, square it, times the function. And how long I'm going to remember that formula, I'm not particularly sure. The variance is a weighted average of the square of the deviations. Okay, standard deviation is the square root of that number. Positive square root of that number. Notice that I did not divide by the number in the sample anymore. Isn't that great? So now I've got my numbers. I have the probability of my numbers. I come up with an expected value, the summation of those guys. I find my variance. So I find that from the expected value, I find the variance. And here it comes. And there it is. I sum them all together. There's my variance. I take the square root of it. Oh, there. I have the standard deviation of the daily sale of the televisions, and why I have it in 5 significant digits, I have no idea. That would make no sense at all. 1.3 would make a lot of sense. 1.2884 would make absolutely no sense at all. I'm only selling 1 to 4 TVs, 0 to 4 televisions. Binomial probability distributions. Okay, so the experiment exists in a sequence of n of identical trials. The outcomes are either success or failure. Flipping a coin, head or tail, success or failure. The probability of success is denoted by a p. Okay, I'm flipping a coin. Probability of success is 50%. It does not change from trial to trial. It doesn't matter how many times I do it, I get the same p. The trials, however, are independent. It doesn't matter what I did before to what I'm going to happen before. Our interest is in the number of successes occurring during the trials. I'm very interested. The X denotes the number of successes for the trials. And just what we wanted to see. So the probability function, n factorial, divided by x factorial, n minus x factorial. The probability raised to the x power, 1 minus p raised to the... Now, that's going to be a very interesting number to put in there. And a number of experimental outcomes providing exactly x successes. Yeah, I'd say that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. About 20 keystrokes, not counting the numbers you're putting in. Yeah, all right. Well, the probability of the particular sequence of successes. Well, the number of outcomes. This is the combination again, right? And n factorial x and minus x factorial comes that way. All right. Evan Electronics is concerned about low retention rate of employees. Hourly employee. Oh, they just fired all the baristas at my Starbucks. I don't know what the probability of that is, but you know, when you train them to steal money, they steal money. You know. So we're going to choosing 3 hourly employees at random to find out what the problem is. Okay. Let's see. The probability of the first employee leaving is P. The probability of the second employee leaving, 1 minus P. And the third employee staying. So leaving, staying. Okay, so the probability of staying is P. The probability of not staying, 1 minus P. Okay, so that's what that's saying. There's the probability of not being there, probability of being there. All right, so 10% of them stay, 90% of them don't. So the 10 minute blah, 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 third trial. So given that I have a stay, leave, 0.081. chance of that happening. I could have an FSF and an FFS or whatever. 2 other experimental outcomes also result in in 1 success and 2 failures. That's right. So we have 1, 2, 3 possibilities of 2 failures and 1 success, and I get to add them all together, 0.3, 0.243. Still not good. What is Evan going to do? So I've got the probability is 0.1, the number is 3, I'm only keeping 1. I throw it through my big calculation, I get the same number, 0.243. All right, now I'm going to do it with a leaf diagram. Leave, stays, leave, stays. Worker 3. Might leave, might stay. Might leave, might stay. Okay, so if everybody leaves, all 3 left. If everybody stays, all 3 are there. One more. The probability. That's because there's no one, everyone stayed.
Oh,
Right. So 0.9 times 0.9 times 0.9. Is that number? I don't know. 0.9 times 0.9 times 0.9. Yeah, that's that number. So leaving is 10%. First worker leaves 10%. Second worker leaves 10%. Third worker leaves 10%. 0.1 times 0.1 times 0.1, 0.001, and 3 have left. So that's what that's saying. The probability of only 2 leaving is the same. It doesn't matter which one left. We ended up with the same probability. So statisticians can develop tables that give probabilities and cumulative probabilities for the binomial theorem. These are in our textbooks. Let's see if I got one in mine. Oh yeah, there we go. Binomial probabilities, page 60, 622, 623, 620, starting at 615. So if I have 2 possible outcomes, the probability of getting 0, 1, and 2 are given by the probabilities in my table. So I may have to go to my table to get some number. That's fine. It's in the back of my book. Modern calculators can do it too. None of us have one of them. They're talking about the TI-80, 86, and 89, and 92 plus. We don't have those. The 84s and 83s don't do that. Okay, so we have an binomial probability, expected number, n times the probability. variance, n times the probability times 1 minus p, and the standard deviation square root of the variance. So we have an expected value of 0.3 employees out of 3. Variance 0.25, 0.7. Standard deviation, the square root of that. Poisson probabilities, yeah. Useful to estimate the number of occurrences in a specific time or space. So we have discrete random variables. We have an infinite sequence of values. Examples: the number of knot holes in 14 linear feet of pine. Oh, that's a great example. I lived in a house in Maine that we bought. It was built in 1820, and it had hardwood floors, and there were no knots in the wood. Still virgin lumber. The number of vehicles arriving at a toll booth in 1 hour. Bell Labs use these distributions to model the arrival of phone calls, so they know how many lines they have to put up. 2 properties. The probability of an event is the same for any 2 intervals of equal length. Okay. So for the next, the number of people coughing in the last half hour and the number of people coughing in the next half hour, the probability it should be the same. We shouldn't have changed our behavior in that regard. The occurrence or non-occurrence in any individual is independent of the occurrence or non-occurrence. So just because something happened a half hour ago doesn't mean it's going to happen next half hour. And there we go, just what we wanted to know. So our probability function, U is the mean of the occurrences, E is the base of the natural numbers, and the factorial guy. That means that means it's time to stop for a moment. We have something else to do here. So, anybody know what pi is?
3.14.
Anybody can give me pi past 3.14? Is it 4.5? Or is it
3.14159264?
yeah, 9265. Who gave us pi? The ancient Greeks gave us pi. Pi is a transcendental number. It never repeats itself. It goes over and over again. It never repeats itself. It goes on forever and ever. They thought it was around 3. That was their pi. So now it's the part. Anybody remember what happened in 1492? Ooh, right. So 1492, Columbus sailed at the ocean blue. 1565, there a man is still alive. What happened in 1565? Magellan circumnavigated the earth. No, he didn't. He got himself killed off in the Philippines, but his boat made it back without him. So now the issue is, did the ancient Greeks know that Columbus was going to sail the ocean blue in 1492? And the answer would be no, because the ancient Greeks didn't have a decimal numbering system. We didn't have a decimal numbering system until 600 AD. So we wouldn't have written pi out that way. All right, so how do we get there? Well, 2.71828 1828 is E, the base of the natural logs. So now the issue comes, 1828, 1828. What was so important that 1828 about that year, 1828? Anybody know what really important thing happened that year that changed our lives forever? Sitting there in the base of the natural logs. After a thorough search of all history books that I took over 20 minutes doing, I found that the only thing of significance that happened in 1828, and it happened twice, was New York City and Boston started the first public high school in 1828. And without public high schools, we'd never be where we are now. No, we would still be going to third grade and going out and getting a job, just like great-great-grandpa did. Okay, well, back to our transparency. So that's my base of the natural logarithm thing based on my story of pi. All right. Maybe you'll remember some of that, maybe you won't, who knows. So I would hope that if I look in my book, I would find a table of this particular function, just like I did of the last guy. And I do. Starting on page 625, I find the Poisson probability table with mu's and x's, and isn't that convenient? So when I need the number, I can go get it. I don't necessarily have to calculate it. And since there's no stated upper limit of the number of occurrences, the probability function f of x is without limit. So it could go very high. In practical applications, x will eventually become large enough so that f of x is approximately 0. So if I go back and look at that thing and say e to the minus x is going to go by. Okay, so patients arrive at the emergency room at the rate of 6 per hour on the weekdays. What is the probability of 4 arriving in 30 minutes? All right, so using the probability function, I have 6 an hour means 3 every half hour. X is really 4, so I end up with 0.168 is the probability of having 4 show up in a half hour. I'm supposed to have 3, I have 4. That would be my probability. Other than I'd want that formula to be on the board. And then I have, I can make a graph of those probabilities if I wanted to. That's not a normal distribution anymore. It's a different guy. The mean is equal to the variance. Isn't that cool? The mean and variance are going to be equal to each other in this type of probability distribution. Variance for the number 3. Hi. Hypergeometric probability distribution. Someone's just pulling your leg, right? Someone just making these things up, putting in the transparency. It has to be that way. Is closely related to binomial distribution, but somebody out. What happens is that every time somebody gets a PhD, they had to add something to the knowledge base, so they wrote some paper about something, and now it ends up as standard practice. Yeah. The trials are not independent of each other. So I flip my coin, and on the way up, it gets shaved by some wombat up here, and it doesn't drop. It's the same coin. And then I flip it again. Now it's not independent anymore. because somebody was doing something. Probability of success changes from trial to trial. Okay, so I'm a football team, right? I'm going to win or lose, and I win my first 5 games in a row. What are the chances of me winning my 6th game? Am I going to? They're out to get me now, right? So I'm going to have less probability of winning the 6th, 7th, 8th, and 9th game. And if I go to the Super Bowl undefeated, I better be really good, otherwise they're just going to get me. So here's my probability function. We recognize these things as the combination thing, the combination of r things taking x at a time, of n things taking n at a time. So that's what that nomenclature means. X number of successes, number of trials, probability, number of elements in the population, and X has to be less than the R. Okay, number of ways an element can be picked out, number of ways of success. All right. The probability function, previous slide, usually applicable to values that are whole numbers. But we have to have x less than r, and n minus x has to be less than capital N minus r in order to be valid, because we can't, if we think about what it means, take 10 things 3 at a time, can I take 3 things 10 at a time? So that's my notation, my notational problem there. So now we're doing batteries. As we move 2 dead batteries from his flashlight, and he's mingled them with the good batteries. All right. He randomly selects 2 out of the 4 batteries. What's the possibility that he gets the good ones? I don't know. What's the possibility that I'm going to open my peanuts and eat them? All right, so 0.168 is the possibility that he's going to get 2 good batteries. So that's not good. So don't put your good batteries inside your bad ones.
Are they dividing?
And so we'll move back. Move back again.
The r over x?
Yeah.
Are they dividing so that 2 over 2, is that
So,
dividing?
No. No. Okay, we'll get out of there. Come to here. N, R, the combination. So the combination of 10 items taken 2 at a time would be 10, 2. Your calculator has that. So you go to your calculator and you go, as soon as I find the right button, okay, I found the right button, and I'm going to take 10 items, 2 at a time, and I'm going to have 45 different combinations of those 10 items 2 at a time. And then mathematically, that's that would be 10 factorial divided by 10 minus 2 factorial times 2 factorial. But I wouldn't go and do that factorial notation in my calculator. I use the combination key in my calculator. So the combination of 2 things taken 2 at a time should be 1.
What's the combination button look like?
I gotta get out of my chair and tell you to have those holes, or you actually have that key right there.
Well, let me see it.
So 10 things, 7.5 You actually have that combination key on your calculator.
Where's my 8?
Yeah. And the graphing calculators all have that. And yeah, your calculator has that. Yeah. Otherwise, we're stuck with doing this factorial notation, which is going to end up giving us the same answer.
So when you see two numbers like that, you just,
Like this.
yeah.
Yeah,
you're just-
that means you're using a combination notation. Yeah,
Okay.
exactly. So when you see that notation, it means that in your calculator, which means that if you're going to do it by hand. So if I go 10 factorial divided by 8 factorial times 2 factorial, well, 10 factorial would be 10 times 9 times 8 factorial divided by 8 factorial times 2 factorial. Those guys go away. 2 goes into 90 45 times. So I can do that in my head. I may not be able to do other things in my head, but I can do that one in my head. But it was nicer to be able to do it on my calculator. But this is saying 2 things taken 2 at a time, 2 things taken none at a time, 4 things taken 2 at a time. Okay. The mean and variance and the hypergeometric probability are those two guys. Isn't that lovely? Well, I'm probably not going to remember that either. So the mean, one good battery. The variance, 0.33. So we have n trials, p is the probability, r over n, of success, population size. If the population size is large, then that's going to approach 1. The expected value is NP, the variable is that guy. All right, well, that's good. Excellent. Excellent, excellent. All right. We have some time to do some homework problems, and then we will pass out a quiz. How's that? So what homework problem do we get to do first? Number 5. I thought I was going to get to my thing before you told me. Number 5.
I just downloaded it, that's all I have.
Let's see. You just downloaded it. Okay, I found number 5. To perform a certain type of blood analysis, lab technicians must perform 2 procedures. The first procedure requires either 1 or 2 separate steps. The second procedure requires either 1, 2, or 3 steps. List the experimental outcomes associated with the performance of the blood analysis. Okay. So we have procedure 1 can be either true or false. Procedure 1, step 1. Procedure 1, step 2 could be true or false. Procedure 2, step 1 procedure 2, step 2, procedure 2, step 3. Could be true or false, true or false, true or false. Okay, that's how I would see that, I think. 2 separate steps. Second procedure requires either 1, 2, or 3 steps. So I don't necessarily have to do all 3 of those. List the experimental outcomes associated with the split test. If the random variable of interest is the total number of steps required to do a complete blood analysis, show the value of the random variable, show what value the random will assume for each of the experimental outcomes. I'm going to come back to the A guy. I think the A guy is going to be procedure 1-1, procedure 1-2, procedure 2-1, or procedure 1-1, procedure 1-2, procedure 2-1, procedure 2-2, procedure 1-1, procedure 1-2, procedure 2-1, procedure 2-2, procedure 2-3. So I think there's 3 outcomes of the experiment. First procedure requires 1 or 2. Bummer. I'll do it again. So the first procedure could be P1, 1, or P1, 1, P1, 2. Okay. I think it's time to do it with a graph. What do you think? P1. No, I don't think so. P11, P12. All right, now that I did P1, I could then do P2, 1. I could do P11 with P2, 2, P11 and P2, 2. Or I could do P11 with P21, P22, P23. Either 1, 2, or 3 separate steps. In the second procedure, either 1, 2, or 3 steps. All right. And then I'd do the same thing. I could say procedure 1, 1, procedure 1, 2, with procedure 2, 1, and procedure 2, 2, or procedure 1, 1, procedure 1, 2, with 2, 1, 2, 2, and 2, 3. Now I think I have them all listed down. All right. If the random variable interest is the total number of steps, all right, so our interest is that we have 2 steps, 3, 4, 4, 5. So that's our random variable. Show what value of random variable will assume for each experimental outcome. Okay, I'm done. So I'm going to go 2, 2, 3, 4, 4, 5. Those are my only outcomes. The number of steps. Okay, so I could get away with 2 steps. I could have as many as 5. All right. 1 down, 1 to go. Oh, what's the next one?
One.
11. A technician servicing milling machines at a company in Phoenix is depending on the type of malfunction. The service call can take 1, 2, 3, or 4 hours. The different types of malfunctions occur at about the same frequency. Develop a probability distribution for the duration of a service call. Depending on the type of malfunction, the service call can take 1, 2, 3, 4 hours. The different types of malfunctions occur at about the same frequency. One, 2, 3, 4 hours, some probability, and they're all going to be about the same. So there's my probability distribution. Draw a graph of the probability distribution. Thank you very much, I just did that. Show that your probability distribution satisfies the condition requiring for a discrete probability function. Yeah, I think so. So the probability of X is A. There's A. So is there more on the next page? Oh, bummer, there's more on the next page. So now we're all the way up to delta. What is the probability that a service call will take 3 hours? Probability of a 3-hour call is 0.25 because they're all the same. 1/4. A service call just came in, but the type of malfunction is unknown. It is 3 p.m. and the technician has to be off at 5. What is the probability that the service technician will have to work overtime to fix the machine? Okay, E. Okay. So 1 hour he can fix it, 2 hours he can fix it, 3 and 4 he can't. The probability of overtime. %, because 3 hours or 4 hours won't do it. And that would be half of them. Okay, next problem.
Wouldn't it be 75%?
No, because he could do the 2-hour one.
Well, if he starts at 3.
And he goes to 5.
Oh, sorry, yeah.
Yeah. Now you could say, well, I'm calling him at 3.
Yeah.
He's not going to get there in 3:01.
Right.
Therefore, that'd be overthinking the problem. Yeah, that'd definitely be overthinking the problem. There we go. Now I've got my own syllabus up. Okay, so we did 11. Now we're going to go to 17. The number of students taking the SATs has risen to an all-time high. Students are allowed to repeat the test in hopes for improving their score. The number of times SAT is taken 1, 2, 3, 4, 5. So my oldest daughter only took it once. My son only took it once. My third daughter only took it once. My youngest daughter took it 5 times. Why? Well, by the time I got to my last daughter, it was clear that there was scholarship money out there to be had if you score high enough. So we made her take it. She was 5 years away from the third sibling. So when she started high school, there was no competition in high school with her other siblings. And so she started taking the SAT and as a freshman. She took it as a freshman, sophomore, junior, twice her senior year. She had to beat 1380 in order to get an $8,000 a year scholarship at University of Connecticut. Otherwise, we weren't going to send her because it's too expensive. And she did. So she got to go to the University of Connecticut. So that's why you take it more than once. I never took it. My generation normally didn't take the SAT. The few of us that went to college took the PSAT, and that was good enough to get in, and that's all that mattered. Okay, back to what? Let X be the random variable indicating the number of times a student takes the test. Show the probability distribution of the random variable. Okay, so first of all, I need the summation of all the numbers. Summation of the number of students. So I'll get that number first. Maybe I'll get that number first. 721,769. 601,325. 166,736. 22299. 6730 equals. So I've got a total population of 1518859. Okay, so I've got 1, 2, 3, 4, 5, and the probability of X is what I'm going to calculate. So I'm going to take, I'm going to give myself more room. 1, 2, 3, 4, 5. Okay. So I'm going to go 721,769 divided by 1518859. I'm going to go 601,325 divided by 1518859. I'm going to go 166,736 1518859. And go 22299 1518859. And then 6730 1518859. Okay, so that's what I'm going to do. And I'm going to call that the probability of X. Okay. There should be a way for me to store a number in my calculator, so making it easier, but I can't think of what it is. 769. .475. 0.396. Point 110. Point 015. Point 004. And then I'd sort of like those guys all to add up to 1, and it looks like they are. If they didn't, I'd go back and go with 4 significant digits so I could get closer. But yeah, they add up to 1, so that means I'm happy with that. What is the probability
I'm looking for
721,769.
the probability of a Coke in my pocket?
Zero service calls.
No, what we'd want to do is we'd want to make a graph. One, 2, 3, 4, 5, and that could be 1 up there. Well, that can be 0.5 up there, and then we could go boom. Something like that. What is the probability that the SAT, that a student takes the SAT more than once? More than once. B. So it'd be 1 minus the probability of only taking it once. So 0.525 would be the probability of taking more. What is the probability the student takes it 3 or more times? 3 or more. 0.004, 0.015, 0.11. 0.0, no, not 0.0, 0.129, 3 or more times. What is the expected value of the number of times the SAT exam is taken? What is your interpretation of the value? Okay, so we want to find the expected value and the expected value is going to be the summation of the times I took it times the probability guy. All right. So it's going to be 721,769 times 0.475 plus.
That thing between the two axes.
Where? Function. That's an f. F of x, yeah. Plus 601,352 times the probability 0.396 plus 166,736 times 0.11 plus 22299 times 0.015 plus 6730.004. Okay, so that's my expected value, mu. And now it's just a matter of executing it on my calculator without fat fingering a key. Okay, and I have 5,99678 would be my expected value. How do I interpret that value? Well, half the people should be above it and half the people should be below it. And so that's how I'd interpret it. Half above, half below. Not really, but what is the variance? So I need the variance. All right. So now I got to get the summation of x minus mu squared times the value of the function. Yeah, that's going to happen today. All right. So, okay. Yeah, that's what we got to do. 721,769 minus 59967. 599,678 squared 0.475 plus 601,325 minus 599,678 squared 0.3, is it 6996? That's a learning disability showing up there. And okay, next one, 166,736 minus 599,678 squared, is it 0.11? I think it's 0.11. 22299 minus 599,678 squared 0.015. 6730 minus 599,678 squared 0.004. Okay, that's going to be my variance. Okay, maybe my calculator will do that without complaining too much. All right. parentheses. 721,769 minus 599,678 close parentheses squared times 0.475 plus parentheses 601,325 minus 599,678 close parentheses squared times 0.369 plus do it all right, parentheses 166,736 minus 599,678 close parentheses squared times 0.11 plus parentheses 2229 minus 599,678 close parentheses squared times 0.015 plus, oh bummer, I ran out of room in my calculator.
Can't you do each line individually?
Yeah.
Or add them all together?
Yeah, I'm gonna have to move back. Okay, I can have the first 3 lines in my calculator. So I got 2.76997 times 10 to the 10th plus last 2. Okay, so I can go second function answer plus, so I didn't really have to write that down, close parentheses 22299 minus 599,678 close parentheses squared times 0.015 plus parentheses 6730 minus 597,678. That's not right. 599,678 close parenthesis squared times 0.004. Okay, I think that my variance is 3.41 times 10 to the 10th. That's my variance. Then I want the standard deviation, which would be the square root of the variance. Second function, and so my standard deviation is 1.84679, and then I have to ask myself how many significant digits do I want. So I take the square root of the variance, and then I'd have the standard deviation. Move up, move down.
So that bottom number is the final answer.
No, 2 final answers,
Which one?
because it wanted that one and that one.
Okay, then what about the one above that?
Well, this is something that I wrote down on my calculator to keep track of it.
Oh, that's not it.
Yeah. So I put that down, but I didn't need to, because I could use answer plus and
Okay, can you hold on a second?
yeah.
Here, you can write it down.
Move back down. You can't have it both ways, you know. Well, you can have it both ways. I don't care.
No. I was wrong. Yeah. Sandra.
Okay. Oh. Oh, here we go. Okay. Anybody got an answer to one? Delta is correct, yeah. All right. Okay, problem number 2. Uh, 20% of that. So 0.2 times 100 which is 20. 20% of students in a class of 100 are planning to graduate. The standard deviation of this binomial distribution. And I don't doubt if any of us remember that particular thing. Binomial distribution. Okay, so I found on page 214 N P 1 minus P square root. All right, so the number in the class is 100. The probability is 0.2. 1 minus 0.2 is 0.8. Square root of that whole mess is 4. What could have been? What could have been more obvious? Now, without the formula, there's no getting it. But
Where was that formula at?
page 214, the bottom of the page where it says variance, standard deviation is the square root of the variance. So to answer your question directly, it's not there. But if you know that the standard deviation is the square root of variance, then you know where it is. Okay, 2 down. Okay, anybody got one for 3?
Okay.
Hearing no objections, we'll go with A. Number 4.
B.
I can go to 4. Oh, I don't have 4. B is correct for 4. Now, it says the expected number of new clients. And if I go and I look at the probability, I see I can have as many as 6 new clients, right? So that means it can't be 21. It can't be 0 either. And it can't be 6. So there's only one thing it can be, and that's Charlie. So when I look at the data, okay, so I'm looking at the data, and it can't be 21 because I only have 6 of them. It can't be 0 because that's not very many. It's got to be something in the middle. So the only guy in the middle was the 3.05. So that was cool. Okay, put your name on your paper, put your test score on your paper and turn it in. And why don't we look at the grade book for a moment. Make sure that whatever your objection is, it's not there.
How did 0.05 come about?
And you're Tara, right?
Did a dog walk in the building?
Now I see a 87
Maybe
is
mine
what I see. So I see 100 in the homework and quizzes, 100 for that thing, 100 for that quiz, 100 for that quiz. No, I don't see any empty spots in the grade
Okay.
book. So I see an 87.
All right.
All right, no problem.
So how how'd the 0.05 come about
Ooh,
on that answer?
On the
Number-
last question,
On the last
number
question.
5,
how do I calculate it?
Yeah, how'd you get that?
I got it because it can't be 21.
Right, I understand that it can't be
It can't
21,
be
and
6.
why can't it be 6?
Well, if I look at the probability distribution, 6 is a 5% possibility. Can't be 6, and it can't be 0. It's got to be something between 0 and 6.
I gotcha. So you found the mean or the
Yeah.
median?
You
Or the,
mean-
yeah,
Now-
the mean.
Now,
No,
if I
the
were
point.
going to
Oh,
do
okay,
it,
I gotcha. The 3 point.
Yeah.
I gotcha.
let me. The question is, if I wanted to calculate it, how would I calculate it? Right.
Right.
That's the question. Okay, so we get back over here. We need the summation.
Oh, okay. Yeah. All the.
And then you add
Yeah,
them all
the
together.
summation
And then
of
you
the
divide it
number
by
By
6.
6.
times
Wouldn't it be divided
that.
by 7?
No,
6.
no. So I got 0 times 0.05 plus 1 times 0.1
Oh, plus 0. Okay, I
plus
get it.
2
I
times
get it.
0.15
Yeah, and then
plus 3 times 0.35
Right.
And 4 plus
plus 4
4 times.
times 0.2 plus 5 times 0.1 plus 6 times 0.05. And I imagine that if I did that math, I would come up with 0.05.
Okay.
okay,
Gotcha.
that makes sense.
That makes
I got
sense.
But because I had a multiple choice test where I
Right,
had
you
three
just
totally
knocked it out.
wrong answers,
Right.
I'm not going to bother doing the math. Thank you very much. Thank you very much. And I'll turn this off.